In this video, we'll talk about AC power. In particular, we'll talk about transmitting AC power and why power factor is important. Recall from the textbook and the lecture videos that average power is, at least hopefully, converted to useful work. Reactive power, on the other hand, is simply traded back and forth among electrical components. In general, we don't get any real benefit from reactive power. However, there's still a cost associated with transmitting reactive power. We dissipate power in the process of delivering it through a transmission line. The power factor quantifies, in some sense, the relationship between average and reactive power. A high power factor corresponds to a power that is mostly average power, while a low power factor indicates a power that's largely reactive. In this video, we'll do an experiment to illustrate the effect that the power factor has on the efficiency of AC power transmission. This is the fundamental problem we're concerned with. We're delivering AC power to some load with an impedance Z sub L. Typically, this load's using the power we're sending it to perform some work, running a motor in a factory, for example. Since we're talking about AC power, all of the signals involved are sinusoidal, so they can be represented by phasors. The voltage in this circuit has a magnitude V sub m and a phase angle theta V. The current has a magnitude I sub m and a phase angle theta sub I. Keep in mind that the relationship between the voltage and the current is set by the impedance of the load. The average power delivered to the load is the RMS voltage times the RMS current times the cosine of the phase difference between the voltage and the current. This cosine theta V minus theta I term is called the power factor. A low power factor implies that very little average power is delivered to the load relative to the amplitudes of the voltage and the current, while a high power factor implies that the average power delivered to the load is large relative to the voltage and current amplitudes. To see why the power factor is important, let's look at this representation of a typical power delivery system. We're generating power with some voltage source. The power is delivered to our load via a transmission line which has some resistance R sub T. The average power delivered to the load is used to perform useful work. However, reactive power delivered to the load is simply traded back and forth between the load and the source. It typically doesn't serve any useful purpose. However, trading the reactive power back and forth does cause power dissipation in the transmission process. This power is just lost. We don't get anything for it. Keeping the power factor of the load high reduces the reactive power traded back and forth between the source and the load, which reduces the losses associated with trading this power. Now let's look at an example that we can implement to get some insight into what's going on. Specifically, our implementation of the previous system has a load which consists of a resistor and an inductor. The case of an inductive load is considerably more common than a capacitive load, so this is a fairly realistic example. What we'll do is create a circuit which looks like this system, measure the voltages and currents in the circuit, and compare the average power delivered to the load with the power dissipated in the transmission process by this resistor R sub T. This is the physical circuit we'll create. The load consists of a 20 ohm resistor and a 1 millihenry inductor. Our transmission resistance will be represented by a 10 ohm resistor. We'll use channel 1 of our waveform generator as our source. We'll apply a 17 kilohertz sinusoid to the circuit. We use channel 1 of our oscilloscope to measure the voltage across the source and channel 2 of the scope to measure the load voltage. The current through both the load and the transmission line can be calculated from the source voltage and the load voltage. This current, along with the measured load voltage, can be used to calculate the average power delivered to the load. The power dissipated by the transmission process can be calculated from the source current and the transmission line resistance. Now let's look at the physical circuit and make some measurements. Here's our physical circuit. This is our 1 millihenry inductor and our 20 ohm resistor composed of two 10 ohm resistors in series that constitutes our load. This 10 ohm resistor is our transmission line. We're applying power with channel 1 of the waveform generator. Ground is here, and I've jumpered ground to the terminal of the inductor to here. Channel 1 is measuring our input voltage. Channel 2 is measuring the voltage across the load. I've set up the waveform generator to create my desired 17 kilohertz signal with a 1 volt amplitude. I'll click Run to start applying voltage. We'll start acquiring data with the oscilloscope. On the scope, I've displayed my applied voltage and the load voltage on channels 1 and 2, respectively. The current is displayed on a math channel. Therefore, the load voltage and current are shown on channel 2 and the math channel. I've set up some measurements here to provide RMS levels of these two measurements. To determine the power factor, we can measure the phase difference between the load voltage and the load current. I've set up these cursors to give me the time delay between these two signals. The phase difference is this time delay divided by the period of the signals times 360 degrees. The average power delivered to the load is the RMS voltage times the load RMS current times the cosine of this phase difference. Since our transmission line is represented strictly as resistance, we can get the transmission line's power dissipation by squaring the RMS current and multiplying that by the transmission line resistance. Now let's take a look at the result of all this number crunching. Here's a summary of the results of our data analysis. Our phase difference between the load voltage and the current is a whopping 78.4 degrees, which results in a power factor of only about 0.2. Using this power factor along with our measured load voltage and current results in an average power delivered to the load of about 0.9 milliwatts. The power dissipated by the transmission line resistance is pretty big compared to the load power, about 0.4 milliwatts. Ultimately, for this case, it turns out that the power dissipated just in transmitting power to the load is about 44% of the power that the load uses. This is awful. So let's take a look at one way to make our power transmission more efficient. Let's try to correct our power factor by adding a capacitor in parallel with the load. We'll use a 0.1 microfarad capacitor. Our goal in adding this capacitor is to reduce the imaginary component of the load impedance. This should reduce the phase difference between the load voltage and the load current and thus increase the power factor. Ultimately, we want theta V minus theta I to be close to 0. Our waveform software settings are the same as for the previous circuit. I just need to plug the capacitor into our circuit and note the differences in the readings. With the capacitor in place, our voltage and current are now almost exactly in phase, so theta V minus theta I is almost 0 and the power factor is nearly 1. Notice that the amplitude of the current has also decreased significantly. Let's compare the results of this situation with our previous results. Notice, as I mentioned previously, that the power factor is now close to 1. The amplitude of our current has also decreased drastically to about 1.5 milliamps. The average power we're delivering to the load is about the same as we had before. The difference between 0.9 milliwatts and 1 milliwatt is probably insignificant since it's difficult to measure these small currents accurately. The trick is that our increase in power factor has allowed us to reduce the load current while still maintaining the same average power to the load. Most importantly, however, is the fact that the transmission line losses have decreased drastically from 0.4 milliwatts to about 0.02 milliwatts. The power required to deliver power to the load is now only about 2% of the power being delivered. We can save a ton of money and energy with this kind of efficiency improvement.